Our topic is nonlinear equations method of calculation.
These are our team members: Isa, Yuna, Julia, Sabrina, Sungwei, Abraham. And next slide is outline. First is the Newton's method. And first, what is the Newton's method? Newton's method is an interactive numerical technique used to find the root of a function, and meaning it helps us solve f of x equals to 0. The method leverages the derivative of the function to rapidly converge to the solution, especially when the initial guess is close to the actual root. The iterative formula is given by like picture. And so this formula uses the tangent line of the function at the current point xn to approximate the curve of the function. And the intersection of the tangent line with the x-axis gives us the next approximation xn at 1. And by repeating this process, we gradually approach the root. And here are the steps. And steps 1 is choose an initial guess, x0. And the step 2 is compute the derivative. Ensure that the derivative exists and is non-zero to avoid division by 0. And Newton's method has a wide range of applications, such as 3. And one is energy calculations. It can solve nonlinear equations in circuit analysis, fluid dynamics, and more. And 2 is numerical optimization. It can find the maxima or minima of a function by solving f of prime x equals to 0. And 3 is physics simulations, modeling nonlinear systems in mechanics and other fields. And finally, let's briefly discuss the error analysis of Newton's method. Assume the true root of the equation is r. The absolute error at the nth iteration is En equals to xn subject r. The error at the new iteration En at 1 is approximately proportional to the square of the current error, like picture. And next topic would introduce the bisection method. And let's start by understanding the method. The formula of the bisection method. The bisection method applies to a function f of x that is continuous on the interval ab and satisfies the condition f of a multiplied by f of b is less than 0. This condition ensures that there is at least one root within the interval, and our goal is to find a value x such that f of x approximates to 0. Essentially, we are narrowing down the interval until the root is found within the desired precision. And before applying the method, the following conditions must be met. And 1 is the function must be continuous. And 2 is there should be a sign change in the interval. And the 3 is the interval must be known. 4 is we assume that the function has a single root in the interval. And 5 is there should be no discontinuities in f of x. And next is application of the bisection method in interpolation analysis. We divide into the 4 steps. Let's go through the steps. And first is let f of 1x and f of 2x be the two functions. And the goal is to find x such that f of 1x equals to f of 2x. And define a new function f of x equals to f of 1x subtract f of 2x. And the next step is select an interval AB where f of A and f of B have opposite signs. This guarantees that there is at least one root in the interval by the intermediate value theorem. And the step 3 is evaluate f of C, and C is equals to A at B divided by 2. And check the sign of f of C. If f of C equals to 0, then C is the root. And f of A multiplied by f of C less than 0. We will update the interval to AC. On the other, if f of C multiplied f of B less than 0, we will update the interval to CB and repeat this process until the interval is sufficiently small or f of C is close enough to 0. And the final step is the point C will be the approximate solution to f of 1x equals to f of 2x. In summary, we will divide into two parts. To summarize, one is suitable scenarios. The bisection method is ideal for solving equations with one root in a continuous interval. And two is limitations. It cannot handle discontinuities or multiple roots within the same interval.
Error analysis. First, we define L0 as the initial interval length, calculated as b minus a, where a and b are the initial bounds of the root. For each iteration n, the interval length Ln is halved and expressed as Ln equals L0 divided by 2 to the power of n. By substituting Ln, the absolute error can be further expressed as the formula on the right. The allowable error E is defined, and the condition on the left is set. This formula shows that the number of iterations n depends on the ratio of the initial interval length, L0, to the allowable error E. Next, the secant method. Conditions for applying the secant method. The secant method has a few necessary conditions. First, continuity. The function f of x must be continuous in the interval where we are searching for the root. If the function is not continuous, the method may fail. Second, uniqueness of the root. Ideally, there should be a single real root x in the interval. Multiple roots could lead to convergence issues. Third, non-zero derivative. The derivative of fx near the root must be not 0. Otherwise, the slope of the secant line becomes undefined. Last, distinct initial points. The two starting points x0 and x1 should be distinct, with the outputs of x0 and x1 are not the same, so the denominator in the formula does not become 0. Derivation of the secant formula. We start with the slope of the secant line between 2 points, which is calculated as the difference in the function values, divided by the difference in the input values, xn minus xn minus 1. The equation of the secant line can then be written as the formula on the left. To find the root of this secant line, we set L of x equals to 0. Solving for x, we derive the formula for the next approximation xn plus 1, which is the formula at the right. This is the core formula of the secant method. Here are the steps to implement the secant method. First, select two initial points. Choose x0 and x1, which are close to the expected root. Second, apply the core secant formula. Third, update points. Replace xn minus 1 with xn and xn with xn plus 1. Fourth, repeat until convergence. Continue iterating until the difference between consecutive approximations is less than a predefined tolerance. About the picture at the left, the graph displays the curve of fx, which represents the target function. The horizontal axis represents x values, while the vertical axis represents fx values. 2 points are marked on the curve. These are the initial points of the secant method and represent the first and second guesses for the root. A secant line is drawn through these 2 points. The intersection of the secant line with the x-axis is marked as x2, which is the next approximation of the root. From x2, the process repeats to compute another secant line and refine the estimate further. Convergence and advantages. In our case, the convergence is superlinear with order, and there are 2 main advantages. One is balanced efficiency. It strikes a balance between computational cost and accuracy. The other is derivative-free. It doesn't require calculating derivatives. Error analysis. Assume that the real roots of the equation are r. The absolute error of the nth iteration is n minus r. At the next iteration, the error can be approximated by the formula below. This recursive relationship indicates that the error at each step depends on the errors from the 2 previous iterations. In summary, the secant method is an efficient numerical tool by solving nonlinear equations. By leveraging the slope of the secant line, it avoids the complexity of derivatives and converges relatively quickly. Conclusion. We compare the convergence characteristics of 3 root finding methods. For Newton's method, the convergence type is quadratic with a convergence rate of p equals to 2. Bisection method. The convergence type is superlinear, with the rate of p approximately equals to 1.618. It's faster than the secant method but slower than Newton's method. Secant method. The convergence type is linear, with a convergence rate of p equals to 1. While it's the slowest in terms of convergence, it is considered more stable. Applicability comparison. Newton's method. The function fx must be continuous. Its derivative must exist and not be 0, and the initial guess must be close to the root. It requires a single initial guess x0. Bisection method. The function fx must be continuous, but the derivative of fx is not required. It requires 2 initial guesses. Secant method. The function fx must be continuous on an interval, and the values at the interval endpoints, fa and fb, must have opposite signs. In summary, while Newton's method is highly efficient, it has strict requirements. The bisection and secant methods are more flexible but may converge more slowly. Thank you.